We now turn our attention to the other end of the Hubble sequence, the elliptical galaxies. In Hubble's definition, ellipticals were old, boring systems containing just old stars with no star formation, no dust, no gas, and the first theories of their formation were that they formed through single monolithic collapse of giant proto-galaxy where all the stars were made. Turns out all of these are incorrect. The modern view is that ellipticals are actually fairly complex systems. They do contain lots of gas, except most of it is X-ray gas. Sometimes they have star formation. Sometimes they have dust lanes. And they probably formed through hierarchical merging of smaller pieces, although dissipative collapse was probably also involved. They're also not simple systems. They have subsystems, just like spiral galaxies do. Some ellipticals seem to show weak disks. Some have special decoupled cores in the middle. Most of them have supermassive black holes in the centers. One important distinction between ellipticals and spirals is that whereas spirals contain most of their kinetic energy in the ordered rotational motion, in the elliptical galaxies, most of the kinetic energy is in the form of random motions. So we call them pressure-supported stars moving like molecules in gas. And here is a blatant example of dust in elliptical galaxies. This is an elliptical galaxy in NGC 1316, which is in the center of the nearby Fornax cluster. The reason why it has all this dust is that it gobbled up a spiral galaxy which had plenty of dust in its disk, and so that's still being digested somehow. We do see a signature of mergers in ellipticals, and a particularly interesting one is so-called shells. If you turn the contrast up in some of the elliptical galaxies, you see these shell-like structures at outer radii. And now we think we know where they come from. If you have a largely two-dimensional stellar component set, such as this galaxy, and then you merge it into an elliptical galaxy, the stars will still stay on a sort of two-dimensional surface until sometime later. And so what we see are diluted, stretched, curved pieces of former galactic disks that be now wrapped around the elliptical galaxy as they're being merged in. This has been seen in numerical simulations and certainly in observations. The way we quantify structure of elliptical galaxies is through surface photometry. We measure brightness as a function of radius and azimuth. And whereas this is light, we can then try to convert that into mass through kinematical measurements. The way we quantify structure of elliptical galaxies is first by measuring their radial brightness profiles, so-called surface brightness profiles. And there are a number of formulae proposed to account for the shape of these brightness profiles. The most popular of them is so-called the Vaucouleurs profile. It was invented by Gerard de Vaucouleurs, and it's a purely empirical formula. And it says that the log of the surface brightness, which is luminosity per unit area, behaves as radius to the 1/4 power. Is proportional to radius to the -1/4 power, or sometimes called R to the 1/4 law. There is a parameter, because it's an exponential involved, and that is called the effective radius. And if you tweak the constant multiplying that power law, that radius can be made so that it contains exactly 1/2 of all projected light. So it's sometimes called an effective radius or a half-light radius. And typically, for elliptical galaxies, its value is of the order of a few kiloparsecs, not too different from, say, typical scaling lengths of spiral galaxy disks. So here are some plots of surface brightness profiles in elliptical galaxies. What's shown here is a logarithm of the surface brightness on the y-axis, measured in magnitudes per square arcsecond, versus radius to the 1/4 power. And the Vaucouleurs profile looks like a straight line in those coordinates. Indeed, for some galaxies, it seems to fit remarkably well in at least some part of the radial range. But in the others, it does not. And so these deviations are also of some interest. Other profiles have been suggested, and the one that's currently most popular is so-called Cercic profile, which is a generalization of the ocular profile. That log of the surface brightness goes as radius to the -1/n, where n is some number. And in case of the ocular profile, n is equal 4, so it's proportional to the radius to the -1/4. In case of this galaxy, n is 1, so then you have just traditional old declining exponential. This formula turns out to actually to work remarkably well for elliptical galaxies as well as dark halos, which is a very interesting thing. Its physical origin is not really well understood. It is also purely an empirical formula. Hubble himself proposed a different profile. This is essentially a power law with surface brightness going as 1 of the radius squared, except in the middle, where it's softened. So there is a parameter called core radius. And within that core radius, profile is more or less flat, and then it turns around and goes into the power law. Now, one problem with Hubble's profile, or as originally envisioned, is that it diverges. If you integrate the surface brightness profile in radius, you'll reach infinite total luminosity at infinite radius, and that clearly can't work. So Hubble profile has to truncate at some point. So it's actually quite remarkable that ellipticals can be fit by the same family of profiles that have, say, just 2 parameters. In case of the ocular, it's the effective radius that scales the radial coordinate, and effective surface brightness that scales the vertical coordinate. In case of Cercic profile, there is that shape parameter, little n, which for the ocular is fixed. And if it were always fixed, then ellipticals would be a homologous family of objects. One can be scaled into another. Turns out that's pretty close, but it's not exactly true. And the deviations of that from that are actually quite important. One deviation that we already talked about before is the diffuse envelopes of CD galaxies in clusters. But you may recall that those are really stars that belong to the cluster itself, just co-spatial with the galaxy itself. Nevertheless, if you obtain surface brightness profiles of many, many ellipticals, and then if you fit Cercic law to all of them, and plot the value of the Cercic parameter, n, which in this plot on the left is confusingly labeled as m by the authors of the paper, you find out that that shape parameter, Cercic parameter, depends on the size of the galaxy and by the same token on the luminosity of the galaxy, and goes in the sense that galaxies with larger radii or larger luminosities have shallower profiles. A more direct way to see this is to simply bin together profiles of many ellipticals, average them up, and plot profile that corresponds to a certain bin of luminosity that's shown on the lower right, done by Jim Schombert. And again, you can see that the more luminous ellipticals seem to have shallower profiles. On the other end, near the centers of galaxies, there are interesting things happening. In Hubble's days, seeing an angular resolution simply were not good enough to actually tell what's happening in the inner arc second or so. And nowadays, with Hubble Space Telescope, we can probe the inner portions of the elliptical galaxies. And interesting things are happening there. In some cases, there are coarse, flat density distributions, sort of like Hubble envisioned. In other cases, there are density cusps. Density goes as a power law all the way in as far as we can tell. And those may be related to the presence of supermassive black holes. And carrying on with what happens at larger radii, we see that the more luminous ellipticals tend to be those that have flat cores, and smaller ellipticals tend to be those with cusps. So here is just a collection of surface brightness profiles from Hubble, and they have been divided empirically into those that show core, which are shown solid lines here, and those that look like power law cusps, not in pure power laws, maybe slightly curved, but nevertheless the cusps, and those are shown as the dashed lines. So the shape of the surface brightness profile changes at smaller radii. And so people who study this have come up with a broken power law, or Nuker profile, that has one power law asymptotically at small radii and a different power law asymptotically at large radii, and there is some transition radius between them where one bends into the other. And so here are the examples, what those profiles look like. On the left, you see what happens as we change the inner slope, whereas the outer ones remain more or less fixed. On the right, it's the opposite. We keep the inner slope but change the outer slope. Galaxies seem to fit all over this particular family of profiles. So next we will talk about two-dimensional and three-dimensional shapes of ellipticals.